Before starting this lecture, I'd like to say something about the next week laboratory. Uh, Maybe you already know that next Friday, the 30th of October, in these hours, so 2:30 p.m. to 5:30 p.m., there would be that lab. Okay, so as soon as it will clear to me how many people will enter this lab, it is possible for you to book your seat. Okay, you book your seat directly from your student portal website, I think. Can you confirm this? Maybe you already did this operation for other courses. I don't know, but I think that is can do for you directly from your student portal. Okay, so people who are interested in doing the lab uh, can say book the seat by the student portal. There are limited seats available for the activities due to today's COVID-19 emergency. So please do come if you really want to say follow this practical experience that will be very important for people who would like they gain some insight into the converter operation, real practical converter operation. I think that there will be four labs in a row. So for the next 4 weeks, at least, we get lab on Friday. Okay, and the lab is non-mandatory. You have not to say compile and to write any relationship. There are no extra marks for doing the exercise in the lab. Okay, in the next hours after I finish this lecture, I put on the Power Electronic website the guide for the lab. Okay, so you can read directly what um, kind of experience you can have in the lab. Okay, you have a board in which you have the boost and the back boost already designed. You just to connect the power supply, to connect the load, and to take a lot of measurements. Okay, understanding what you are doing. Okay, this is the goal of this slide. Okay, during the weeks in which there is the lab, I slightly modify the schedule of the lectures. Okay, so for example, next week I will give lectures on Tuesday, and then on Friday morning, and then we have the lab on Friday afternoon. In the successive week, probably I will get lecture also on Monday. Okay, Monday, Tuesday, and Friday morning. Okay, in order to have, let's say, for all of you, 6 hours of lectures a week, except of the lab. Okay, so let's have a look on the website for my communication because well in advance I will communicate you the correct sequence of lectures. Okay, so stay tuned. I have a questions here in the chat. Do you have to book a seat on the website or on the? Oh, okay. I wrote on the as a message in the portal that you have to book on the LED website, but I talked to the people in charge for the lab that they talked to me that you can book your seat directly on your student portal. So I don't know which one is true. Okay, maybe you have more experience than me about this kind of procedure. Have you ever booked a lab directly on through your student portal in these days for other courses? I don't know, but I know that there is the possibility to book your seat on the LED website, on the portale. Okay, so do the you can book from your portal. I can change my message on the portal. I really don't know the exact procedure. Okay, this in this time you have to forgive, but there are a lot of confusion about how to follow lab in person, so forgive me. Uh, for me, it's okay if you book your seat directly by the Portale Students, okay, to the website. So don't worry about that. If you have some problem, you can contact me. Okay. Uh, at the maximum, the LED 5 has 18 seats. Okay, one student for a test bench for a bench. So 18 students can enter. Maybe because it depends also on the number of boards, of working boards that we have in the lab. And this is something that I really don't know at the moment because people in charge in the lab are trying to understand how many boards are available for power electronics. Okay, you have to understand that power electronic boards are not low power boards. Okay, so they have some amperes current that flows through circuits. So there are a certain number of boards that are not working nowadays, but they are working to say repair them, and so I, I I think that maybe on Monday I have the exact number of seats you can book. Okay, at the most 18 book, 18 seats. Okay, so but if you have the possibility to book next week when the situation is more say, clear, even to me, maybe you are more say you can book with confidence next week. Okay. As I said, I will put on the website the guideline for these activities. Okay, I recommend all of you, mechatronics students and students, to follow. Okay, of course, just few students can follow at a time. I'm asking you if you can say record your activities for say your colleagues, maybe your friends, in order to say share these kind of activities to all students. Maybe in the next week you can rotate the book in order to have more students follow attended this. So if you have no questions about these activities, we can continue our discussion about the buck converter. Okay, we started to discuss the continuous current mode buck converter in steady state. So we are just discussing what happens when we have no transient at all. So everything, every electrical quantities are very stable. There are no variations, and so we derive some useful information, and from that information we can continue today. Okay, let me share the whiteboard. Okay, let's continue the discussion about the CCM, which stands for Continuous Conduction Mode Buck Converter, which is also known as step down. So we learned that for continuous conduction mode, the inductor current is always greater than zero during the switching period. So if this is Ts, which is the switching period, the current is, say, something like this, the inductor current. We define as maximum current Imax, the peak value of the inductor current, and I minimum, the minimum value of the inductor current. Both these currents are different from zero in continuous conduction mode. Okay, this first period is called as T on. Okay, and since we define the duty cycle as T on over Ts, this is also called as the duty cycle multiplied Ts. It's the same. Then we derive that the slope during T on, the slope of this current is V in input voltage minus the output voltage V naught divided L, while the slope during the T on to Ts time interval is negative V naught over L. Okay? So from these two slopes, we can define the current ripple. Current ripple is the peak-to-peak variation of inductor current. Okay, and this current ripple is simply, let's say, V naught over L, which multiplies, say, the time interval, which is Ts minus T on. And so this is VO over L, 1 minus T over Fs. In this computation, I used the negative slope of the inductor current, okay, the negative slope that has slope negative V naught over L, okay, but the same results can be obtained using the positive slope of the current. In that situation, I will have V in minus V naught over L multiplied duty cycle Ts, so V in minus V naught Fsl multiplied. Okay, the two equations are equivalent, okay, because you know that we have this conversion ratio, which is the duty cycle between the output voltage V naught over the input voltage for CCM operation. Okay, so this is what we get last time. This is the situation that occurs anytime the buck converter is operated in continuous conduction mode. Remember that we have also derived the average value of this current. Okay, the average value of this current is exactly the output current I naught. Okay, I naught is equal to V naught over R, in which R is the equivalent output load connected to the output port of the buck converter. This is the average current flowing through the inductor. And this is due to the fact that we have no DC current flowing through the C0 capacitor. Okay, we have the inductor, we have the C0 capacitor here, and we have the load. Okay. The current here, IL, here we have a node, the current here is constant current, V0 over R. No DC current can flow through the capacitor due to the charge balance characteristic of the capacitors. So at steady state condition, no DC current can flow through a capacitor. So the DC current I naught comes directly from the current IL. Okay, so in other terms, we can apply the Kirchhoff current law at this node, out node, for the average quantities. So we can get that IL is equal, IL average value, to I0 plus I0 average value. Okay? And so this average value is null through the capacitor. So the average value of the inductor current is directly the output current I naught. So this is the result I show you. So this is I naught. So what happens if we change, for example, the resistance? Okay, if the load resistance change, for example, if the load resistance increases, okay, what happens to the output current I naught? If R is increased, so output current is decreased. Okay, if the output current is decreased, it means that average value of the inductor current gets lower. Okay, goes down. What happens to the peak-to-peak value of the inductor current? The peak-to-peak value of the inductor current, you represent in this way, or if you want to represent it in this way, as you can see, has no relationship with the output resistance, okay, to I naught. So that means that even if you change the load, okay, if you don't change the duty cycle, the output voltage, the input voltage, let's say, and switching frequency and inductance, okay, if all these parameters here for delta IL are the same, the delta IL is constant, okay? So that means that if you change the load, increasing it, you maintain fixed the ripple current delta IL, but you, let's say, change the average value. So if you increase the load, it means that you can have something like this. Okay? The same delta IL, but the average value is decreasing, okay, due to this condition. So eventually it comes a situation in which the minimum current goes to zero, okay? A situation that I can depict this way. Okay, decreasing the output current, so increasing the resistance at the output, eventually comes a situation in which you have a point in which the current goes to zero. This is the minimum possible inductor current that you can have in continuous induction mode. So if you continue to increase the load, okay, the current can go, let's say, below to zero for a certain interval over the period, yes. So this is a condition that we call as the discontinuous induction mode, okay? So the minimum possible, say, the critical situation, the boundary situation between continuous induction mode and discontinuous induction mode is depicted by the situation in which the current IL goes to zero in one single point. Okay, just here and here. This is the situation. So typically, as you can see here, you can get in discontinuous induction mode by increasing the resistance. Okay, increasing the resistance is a situation that can happen, for example, when you disconnect the load. If you remove the load and then you can have infinite impedance, if you want, output current is zero in that situation, you go immediately to discontinuous induction. Okay? Sometimes it happens that converter have to, let's say, design to, say, support situation in which you don't have any load connected at the output. So in that situation, you have to understand that you are in the discontinuous induction mode. Sometimes the same converter are designed to be operated in discontinuous induction mode for any kind of output current, so for any load connected to the output. Okay, so different situations you can meet in practical design. Typically, since discontinuous induction mode is met when you have large resistance and very low level of current, this condition is also known as light mode. Continuous induction mode can also called as the light mode. Light mode means that you have very low current. Okay? The continuous induction mode, for example, can be also called as heavy mode. Heavy mode means that you have large current flow together. Okay? So sometimes in the literature you can have both the name for this kind of operation. So let me again show you what happens at the boundary condition between the continuous induction mode and discontinuous induction mode. The situation is depicted here. This is the CS period. This is on. This is the average value, which is I naught, and this is delta IR. What happens in this situation? This situation is the minimum possible output current that you can have in continuous induction mode. As you can see, the output current is exactly half the value of the ripple current. Remember that we define that the minimum current flowing to the inductor is defined as V0 over R minus delta IL divided by 2. So it is V naught by R minus V naught 1 minus V divide 2 LFS. And this is the minimum current. Minimum current in that situation I depicted in this figure is null, okay? Because this current here. So from that specific equation, okay, from this one, we can derive, for example, the inductance value that leads to the minimum current equal to 0. The L, and we can call this L critical L, as the inductance R divided by 2, 1 minus T, 2 times F. So with the inductance, with the output resistance, the equivalent load R, which is fixed, duty cycle, which is fixed, and the frequency, which is fixed. This inductance defined in this way, which value is defined by this equation, leads to the graph that I show here. Okay, so the situation which is called the critical conduction mode. So the situation between continuous conduction mode and discontinuous conduction. This is also called boundary mode. Okay, when L is higher than this critical inductance, then you have continuous conduction mode. Okay, because if L is greater than this minimum inductance here, then you can have a current which is positive, strictly positive for all the time instant in each period. Okay, so this is a very important condition. I'd like to stress this condition here. If L is higher than R divided by 2, 1 minus V frequency, then we get the continuous conduction. If L is lower than this value, okay, then we operate the converter in discontinuous conduction mode. So this is very important to understand when you design, when you want to select the inductor for your converter. Okay, if you are required to operate in CCM, you have to understand that you have to choose an inductance which is higher than the value defined by this. If you want to operate in discontinuous conduction mode, then you have to choose an inductor which follow these kind of inequalities. Okay. In any case, if the resistance at the output R is, let's say, infinite, so you disconnect the load, you get in discontinuous conduction mode. Okay. So in order to be sure that this kind of inequalities is always true for your operating condition, you have to consider the situation that always happen in which always you have a variation of the duty cycle between a minimum value and a maximum value. Okay, so your duty cycle in your practical converter is not a single value which is called D. Always this value has a range within it can change the value. For example, between the minimum and the maximum. Remember what I said at the beginning of this discussion, that the output voltage typically is fixed. Okay, I have to provide a, say, I don't know, 5 volt, 3.3 volt, 12 volt at the output fixed. For any variation you can have in your environment, in your load, you have to provide this kind of fixed voltage at the output VO. So VO is fixed. But what I said that V is not fixed. V is constant, okay, but can change because, for example, it is derived from a rectifier output, or maybe it's a battery that can change the value due to environmental conditions. I know, self-repaired situation, like that. So pin typically ranges from a minimum value to a maximum value. So if you take into account these two conditions that typically you can write in your design, then you have a minimum duty cycle, which is VO over V maximum, and a maximum duty cycle, which is the ratio between VO and V minimum. Okay? So the duty cycle is typically included in a variation which is from a minimum value to a maximum value. So if you want to be sure that the inductance is always greater during this duty cycle interval, then what is important, and then you can have 1 minus d minimum value, because in that situation you get the maximum difference. Okay, 1 minus d minimum is a very huge value. The switching frequency is constant, so there is no problem. The number 2 is a number, so R is another variable condition, because the load is not fixed typically. This is an equivalent load, is a representation of the ratio between the output voltage and the output current, so at the dimension of that resistance, and this can change depending on the load. Okay, so typically this is not fixed, as it happens for the duty cycle, for the input voltage. Also, the resistance can change from a minimum value to a maximum value, and you should know, say, when you start your design. So in order to be sure that L is always higher for all the operating conditions, you have to put here the maximum. You stay C. Okay. So minimum duty cycle, maximum resistance, and then you can choose your environment. Have you any questions about this consideration? Okay, I can continue. So we get these, we got these results by considering that at the critical condition, the minimum current flow into the inductor is null. So this is V naught over R minus V naught y minus d u LFS equals to. Okay. So we simplify this one, we can get 1, which is equal to y minus d, which multiply R over ULFS. Okay. I'm trying to generalize this kind of discussion, okay, about inductance, etc. So I can, typically what you can find in literature is that 1 minus d is called K critical. And 2LFS over R is called simply K. Okay, so K critical, we can say K critical for the back, because this will be different for any other topology, is 1 minus d. K is 2LFS over. So in the critical situation, you can have this condition. K critical is equal to K. Okay. Let's plot K critical of the back versus the duty cycle. K critical for the back is 1 minus t, so it means that we have 1 here when the duty cycle is null, and then we can have 0 when the duty cycle is 1. Okay? So let's have, for example, K, which is 2L Fs over R, that has this specific value. So K is from in between 0 and 1. Okay? Not well specified, but it is. So since my condition is that at the critical boundary I have K, which is equal to K critical, the back at the boundary, it means that under the curve we are in DCM, and over the curve, over the critical curve, we are in CCM. Okay? For any K which is large than K critical, for that specific duty cycle, we are in CCM. For any K specific duty cycle that is lower than K critical, we are in DCM. So for a K which is in between of 0 to 1, the buck converter will operate in DCM before D star for lower range of the duty cycle, and it operates at CCM in the higher part of the duty cycle. Okay. If you want to include what I said before about the minimum duty cycle and the maximum duty cycle, suppose that I have two working duty cycles, the minimum and the maximum. That depends on the minimum input voltage and the maximum input voltage. So I have this situation 1, 0. This is duty cycle 1. This is again K critical for the buck converter. So if you want to stay in CCM for, let's say, the variation of the duty cycle between duty cycle minimum and the maximum duty cycle, of course, you have to choose a value K which is higher than this intersection point. In that situation, I will be sure that for any duty cycle included in the interval between the minimum and the maximum, I'm always in CCM, which is this part of the graph. Okay? As you can see, this is exactly the same situation I discussed with you before in terms of inductance. Okay? If you want to stay in CCM, having this variation of the duty cycle, I have to choose the minimum duty cycle. Okay? Not the maximum. If you want to be very sure to stay in CCM for any operating condition, okay, 0, 1, 0, 1, okay, you can choose a K which is higher than 1, for example. If K is larger than 1, okay, suppose that you don't know, for example, which is your minimum duty cycle, okay, because you don't have this kind of information in your design. So you can choose duty cycle minimum like 0. So choosing K, which is larger than 1, makes you sure to operate your buck converter, say, always in CCM, for all the, say, possible duty cycles from 0 to 1. This is what happens here. In that situation, K is 2L Fs over R higher than 1 means that L is higher than R over 2 times Fs. Okay, so in this case, if you get, for example, R maximum by 2L, Fs, you are sure that you're working in CCM for all duty cycles. There is a drawback in this discussion. Of course, if you get this result, okay, you are pretty sure that you don't worry about the duty cycle. You are always saying CCM for any kind of duty cycle, etc. But remember what I said before. If I have a duty cycle, okay, then minimum duty cycle, my expression is something like this. Okay, so this is the expression of L that you have to choose when you know the duty cycle minimum. This is when you don't know it. Of course, when you use this expression, the second one, when you have the duty cycle, your inductance here that you can choose is lower than the inductance you can choose here. The inductance here is higher than the inductance you can design here. So this kind of solution brings you choose a higher inductance. And when you choose higher inductance, you have certain drawbacks. First of all, you have to pay more because large inductance in value cost more than lower inductance. Then large inductance typically have a large volume that brings with them large pulse series. Okay? And then they have large volume means that the volume of your converter is larger. Okay? While typically you want to minimize the value, you have to design compact converters. So typically is better to understand which is the minimum duty cycle you have to have, then you have to consider, and then you design your inductance by including the minimum duty cycle. If you are interested in the examination, this kind of information will be always clear, okay, which is the minimum duty cycle or the maximum duty cycle. Okay, so no problem about that. This kind of generalization that I described here with the parameters that are called K and K critical leads also to, let's say, understand, to design other kind of parameters in the back. Okay, up to now I focus my attention about the inductance. Okay, for example here in order to stay CCM, but if you know the inductance, this expression defined by the K, critical case, means that you can also say evaluate, for example, for a fixed inductance, which is the resistance, the load resistance that can be, say, connected to the output to stay in CCM for a fixed inductance. Okay? So you can use this expression, you can invert this expression in order to evaluate, for example, the resistance. Okay, so we can start again about the minimum current, which is 0, to stay, say, at the boundary. This is V naught over R minus V naught over Q1 minus V LFS, which is 0. Simplified, so we can say that R now, solving for R instead of L, means that R should be less than 2 times L Fs over 1 minus D for CCM operation. Okay, so fixed and fixed L, then I can I know which is the minimum resistance that can be connected at the load, meaning the equivalent resistance for say in CCM operation. Both of this situation R and L boundary for operating CCM or DCM are a direct consequence of this generalization that I put here. K is a parameter that is described in this way. So when you choose R as a variable, you can get what I described here. When you choose L, you can get this result. Okay. Of course, you can also derive the solution for the switching frequency, okay? Because the operation in CCM and DCM also depend on the switching frequency you are choosing when you fix the load resistance. Okay. Typically, what happens that is required to design the inductance because the variation of the resistance is already known. Okay, so design specific. So this is for, so we are able to design the inductance to say CCM. Okay, we have I listed more or less the waveform for the current that you can have in the different part of the buck. There are also two currents that I have not discussed that are the current through the capacitors. Okay, let's start with the input capacitor current. The input capacitor is called Cin, so this current is IC. Let me redraw for a moment the branches of the buck circuit that are involved here. So Vin, this node is what I call the active node. We have the switch. Since the switch for me in this discussion is an ideal switch, I can say replace by an ideal switch to the MOSFET. Okay, Vin is here. Let me indicate the current IC in, which is this direction. The switch current is flowing here, and we have the input current. Okay. Of course, here you have the rest of the circuit. We already learned about the waveform of the switch current. The switch current is the same of the inductor current when the switch is on. And the switch is on during T on. When the switch is off, current flow to the switch. Okay. We have a node here to which we can apply the current law, the Kirchhoff current law. I write this law with the letter KCL, which stands for Kirchhoff current law, at node A. Kirchhoff current law at node A says that let me discuss this switch current law for the average quantities. Okay, so for the average quantity, we have that the switch current average value is equal to the input capacitor current average value plus the average value of the input current. Okay, as you can see, as I said last time, the Kirchhoff current rule is a linear operator, and also the average is a linear operator, so we can exchange the summation with the average operation. So the Kirchhoff current rule can be employed for instantaneous value and also for average value. This is an example of application of the Kirchhoff current rule for the average value of the current about the input current? Input current is the current that is output by a constant voltage source. So this current is constant, is a DC current, okay, because it's the current from a DC source. So this average value is the same of its DC value, okay? In that situation, I can say that which is the average value of the input capacitor. Remember the charge balance condition in steady state, no DC current can flow in any capacitor. So what does it mean? That this average value is null due to the charge balance in input capacitance. No DC current flow through this DC current average value is the same. So the average value of the switch current is the input current. The average value here is the input DC current. Okay. So if you want to derive which is the average value, sorry, the current flowing to the input capacitance, okay, we can choose, for example, the Kirchhoff current law for the instantaneous value. We can say that this is a switch minus I in, okay? That is not here. But I in is the same of the average value of the switch current. So now we are able to draw the input current when we know the switch current. Okay. Current flowing through the capacitor when we know the switch current. This is the switch current. Yes, on. This is I minimum, I maximum, the same value of inductance, of course. So we can have I in, IC in is defined by indicated in this expression here. I switch minus its average value. The average value is here, is I in, and so we can say that okay, the input capacitor current is something like this. The maximum is I max minus I input. The minimum value is I minimum minus I in, and we have I negative I in. Okay. This current here has no DC value, so that means that this area here should be the same of this area here. Okay. This is the input capacitor current. So, have you got questions about this computation? Problems, remarks? So, up to now, we defined and we describe all the waveforms you can see in this slide. Okay, I know that there is a DC current, which is the current which is at the output of the DC V in waveform. I have an inductor current from which I started all my analysis. we are in CCM, so this current is always positive for any time instant. Okay. I have a load current, and this load current is constant because the output voltage is constant, so it is V naught divided R. The current flowing to the output capacitor is a current that has no DC current, and so it's simply the inductor current minus its average value, which is not. I have a switch current, which is equal to IL during on, and it is 0 during off. I have a diode current, which is 0 during the on, and which is equal to IL during off. And then I have a current flowing to the input capacitor, which is equal to the current for the switch minus its average value, which is IN. Okay? So as I said at the beginning of the discussion, I said, pay attention that when you are discussing PWM converters or R switched converters, the current are always, let's say, a connection of pieces of linear ramp, or maybe they are constant. This happens here. And if you look at the voltage are always square waves or rectangular waves. For example, here, indicated. From this point on, in order to choose all other components in that buck converter in CCM, we have to little bit understand which kind of parameters I need to choose this component. Okay. Up to now, we just choose the inductor. Okay, we choose this inductor based on, let's say, operating condition in CCM. So we have inequalities, and on the basis of this, we can choose inductors. What about all other components? So let me discuss a little bit what kind of parameters I have to compute to say fully understand which how can choose all other components. Okay. So again, I have to share the whiteboard. Okay. So let's start with the inductor. Inductor, maybe inductance, is defined as the ratio between a magnetic flux and the current I that generates this flux. Okay? These typically require the presence of a loop in which this current can flow. And typically, inductors are made by winding conductors around ferromagnetic core. Okay? So we have a certain amount of loops, like this, around a piece of ferromagnetic core inside here, which has a ferromagnetic permeability, etc., etc. If you look at the curve, so the dependence of the flux with respect to the current that generates this flux, you can distinguish two different regions. There is a first region in which the dependence of the flux with respect to the current is pretty linear. And this is also called for this region linear region. In this linear region, the slope is constant. So that means that the inductance, which is the slope, is constant. Okay? Typically, this is the region in which we have to operate inductor, okay, with constant inductance. If you increase the current, okay, eventually it comes to a point in which the slope here is no more constant. It saturates like this, for example. Okay? So if you look at the slope, for example, here, and you compare to the slope you can have in the linear region, you can say that the slope here is lower. So here, the inductance L prime is lower than the inductance you can have in the linear region. Okay? This region here, you can have this kind of saturation effect. Is called saturation region of the field. Eventually, this curve becomes flat. And so that means that the inductance here is going to zero. So the inductance becomes a piece of wire, short circuit, no more than inductance. So for this region, for these reasons, yeah, it is quite simple to understand that you have to know which is the maximum current for which you remain in the linear region. So E max current is important, okay? Because if you exceed I max, so a current larger than a mass flow in the inductance, then the inductor can become slower and eventually it becomes a short circuit. So this is a very important parameter, okay? The maximum current flowing through the inductor. Okay? Another parameter that is important is also the inductor current ripple, delta I, which is defined, because this kind of parameter is somewhat related to the magnetic loss. So I can say that the maximum current is important and also the current ripple, because this can give you some losses, okay? So these two parameters are important for choosing the inductor, okay? But we already defined both. This maximum current is, let's say, VO over R plus the ripple divided by 2. And the ripple is defined as, let's say, before, is VO R minus V. Okay, so when you choose the inductance, okay, the value of the inductance can be chosen on the basis of the inequalities I defined before, for example, to stay in CCM, but then you also have to compute these two parameters for choosing the data sheets, is the inductance you need. Another thing that I can mention now, even in the future lecture, we don't use it, is to understand that when you have an inductance, we say this as a design, a drawing of an inductance, okay, inductance as lead terminals, okay, that are here. Then you have PCB, these are the terminals. Then you have current flowing here. The current flowing here is a current that, as you can see, okay, is a current that has a periodic variation, like for example, PS, okay, is a periodic current, and it flows through a loop, it's here. So this current, this setup, this arrangement, induces by itself another inductance, okay, which is not inductance with the proper nominal inductance inside the component. The inductance due to this loop in which you have this current flowing at this frequency PS. So if you want, you have a model which is a little bit more close to the reality. You have the nominal inductance L, okay? Then you have some inductance here due to determination, okay, for these reasons here. Then you have to understand that you have some, say, conductors that are wounded around the ferroelectric core, and these inductance bring with them some resistance, okay? So this is the resistance that we can call RL. And then what happens that you have several loops here, one adjacent to the others. So you have, say, change the color here, for example. Okay? You have some parasitic capacitance between each loop to the successive one. Okay? So you have to understand that you have also capacitance here. And then you have also another capacitance due to the presence of the terminals. Okay, so these are two metallic that are separated by a dielectric, which is the hair, for example. Then you can have also a parasitic capacitance here. which is again connecting this way. So the model of a real inductance is a little bit complicated. Okay, it includes all these parasitic effects. Okay, these are the external terminals. So not only the nominal inductance, that you have a series resistance RL, you have capacitors, and then you have this. Typically, these inductance here and the terminal capacitance are not so huge, so you can skip them. In our analysis, I said that this inductance here, this resistance here is, let's say, negligible. So RL is negligible, okay, for our analysis. Remember my assumption at the beginning of this discussion. Okay? And also this capacitance, which is the capacitance here due to the loops that are adjacent, it cannot be considered. So for the rest of my discussion, even for the other topologies, my inductance is pretty uneven inductance. Okay. Sometimes in real situation, real design, practical design, you have to consider this equivalent series resistance RR because it can induce some losses, okay, due to the root mean square curve flow to it. So sometimes this can be a problem, okay. This for inductance. So for inductance, for what concerns our design, you have to consider which is the maximum inductance. So you have to choose the value, then you have to say define which is the maximum possible current flowing through it, and also the maximum default you can have. Okay? These three parameters in conjunction make possible to say choose from a datasheet the inductance. What about the capacitors? Capacitors, which nominally are say described by this symbol, in effect they can be a different kind of construction. I just want to mention two different ways to construct capacitors. One is the electrolytic kind, and the other one is the ceramic type. Okay, so they have totally different kind of construction. Typically, capacitor, ceramic capacitor can be built with the lower capacitance value with respect to electrolytic capacitance. Okay, so this is typically when you choose for a very large capacitance, 100 of microarea or more, then you have no choice. You just have electrolytic capacitance. Okay, for low value, it's better to use ceramic capacitor because some reasons that I'd like to discuss here. Okay, so these capacitance basically are always defined, are always constructed by having, let's say, two metallic plates that face one to the other, separated by a dielectric with a specific dielectric constant. Okay? These are the two terminals. Let's say in the slide I called it the C2 and the C1. Okay, so this for me is C2 and this is C1. And then suppose that these are the external terminal, and then I have internal terminals, okay, that are C1 prime and C2 prime. So which is the equivalent electrical model of this construction? Let's start with external terminal C1 and C2. Again, when you put these capacitance on a printed circuit board, you have current flowing to these terminals, and this current flow to a, let's say, loop. Exactly the same way we discussed today. So we have an inductance here. Inductance due to the termination, in the same way, you have a capacitance terminal, which is due to the fact that you have two conductors here that face one to the other, and then they're separated by IA or something. Of course, this capacitance is very small. It can be skipped. Okay. Then you have, let's say, a large plate, especially if you want to if you are using a large capacitance, large capacitor, okay, with a very large value, this plate can be very large, and so that means that your metallic plates are very large, they bring a very huge resistance with them. This is the resistance of the plates. Then you have the nominal capacitance C, and then you have the dielectric, which has some losses that can be modeled by a resistance scale, resistance of the dielectric. So typically the resistance of the dielectric is so large that you can skip. What you cannot skip are the series inductance, the series resistance, and of course the nominal capacitance. So typically what happens is that in your capacitance you have between terminals C1 and C2, you have inductance, you have resistance, and you have finally your nominal capacitance. This resistance, which is mainly due to the resistance of the metallic plates that say, compose this capacitor, is called equivalent series resistance. The inductance, which is mainly due to the terminal, is called equivalent series inductance. Okay? This is a generic model. This is the model that best fits the behavior of electrolytic capacitance. Electrolytic capacitors can be described in their behavior by a model which is exactly given by the series of ESL, SR, and SC. This is due to the fact that electrolytic capacitors have plates that are very large, bringing with them a very large equivalent series resistance. Okay, so this equivalent series resistance is a mark of the fact that you're using electrolytic capacitor due to the construction. If you are using ceramic capacitor for getting lower value of capacitance, typically this equivalent series resistance is so small that you cannot measure it. So for ceramic capacitors, okay, between C1 and C2, typically you just have these two components. So you have the equivalent series inductance, but not the equivalent series resistance. Okay. Of course, this is my, let's say, approximation. This you have to prove for any components you're using that this is true by looking at the datasheet. But typically, what happens is that the ESR for ceramic capacity is so low that even the datasheet cannot report it as a quantity to be measured. Okay. And also the equivalent series inductance is typically smaller than the equivalent series inductance of electrolytic. Okay. Typically, then you have also kind of components that are called surface mount device. Okay, SMD devices. Surface mount devices are devices that have no lead terminals. Okay, so they are not components like this one. They have some metallization plates on sides that replace the need for these leads. Okay, and this is due for having, say, compact components leading to compact applications because you have no, say, extra space to accommodate these leads. And so the leads are very short that typically also the equivalent series inductance can be skipped at all. Okay? So sometimes this is also something that is not. So, but the main difference between electrolytic capacitors and ceramic capacitors is in the equivalent series resistance. So if I have electrolytic capacitors that are like this. And if I want to put on a graph the impedance of this overall component here, made by the series of these three resistance, inductance, and capacitors versus the frequency, I have a situation which is described in this way. There is a first part of the impedance that decreased like 20 dB per decade. And 20 dB per decade minus negative 20 dB per decade is exactly the impedance of a capacitor. Okay? So here, for this lower range of application, my electrolytic capacitor acts exactly as a capacitor. Okay? Then what happens if the frequency increases? If the frequency increases, then there is the resistance that dominates the impedance. So there is a intermediate range frequency in which we have the ESR, okay? Constant with frequency because our resistance has no, say, frequency dependent behavior. And then for higher frequency, we have plus positive 20 dB per decade. So my electrolytic capacitor acts like an inductance, like the equivalent series inductance. So what happens that, just to give you some numbers, okay, here you have this zero here, and this zero here can have range started from, I don't know, 1 to 12, 10, 15 kilohertz, something like this. Okay? And then you have here a pole, and this pole, let's have also megahertz. Okay. So, which is the typical switching frequency of our component? Typically, is in the 100 of kilohertz. Okay, so 100 of kilohertz. So that means that typically we are working exactly in this region here. Converter works in the region in which my ESR, my output, my capacitors, my electrolytic capacitors are not working as capacitors. They act like resistors. Okay, so this can be, let's say, a problem. Okay, so we have to understand that this kind of effect, parasitic effect in capacitance, leads to some drawbacks. Okay, what happens when you have ceramic capacitance? Ceramic capacitance behave a little bit better because if you look at the impedance versus frequency, then you don't have the effect of the equivalent series resistance. Okay, you have just the equivalent series inductance, and the behavior is something like this: negative 20 dB decade in the lower part of the frequency range, so it acts like capacitance. Then it goes up positive 20 dB, like the equivalent series inductance. Typically, this kind of frequency is, let's say, it can be higher than the value which we are operate the converter. Typically, in the range which we are, let's say, 100 of kilohertz, we are here. Okay, we are here, so we are working with appliance capacity. This kind of behavior has different behavior for electrolytic capacitors and ceramic capacitors can have an effect on our, for example, output voltage. Okay, for our part. Have you questions about? Okay, we have a questions from Cannone Marco. Why we don't have a ESR in some way? This is due to the construction. Okay, As I just mentioned in this lecture, the ESR is due to the resistance of the metallic plates that compose the capacitors. Okay? Typically, the electrolytic capacitors are built in such a way to enlarge these metallic plates, so they can have a large capacitance, okay, but they cannot have. So let me share a simple concept with you, and then we have a break. Okay, uh, even here. So the capacitance depends on the say um, the electric permeability, then depend on the surface of the metallic plates, and then depends on the distance. Okay, so in the electrolytic capacitance, this distance here cannot be very small because you have to insert some materials, which is a liquid material, the electrolyte, that was electrolytic capacitance. And so we have to enlarge S in order to have a say large amount of capacitance. Okay, so since you need this large surface, that is the reason why you have a large equivalence resistance. In ceramic capacitance, the same equivalence, the same expression can be employed, of course, but with V, which can be very small. Okay, so in that situation, you can get the same capacitance for, say, not so large surface S. And so that means that you don't have any so large equivalence resistance. Okay, so this is just for, in a short way, why this happens. Okay, maybe if we have time later, I can discuss with you how electrolytic capacitors are made in details. Okay, this can be interesting, but okay, it's something, say, away from the the discussion I'd like to have for the back. Okay, let's have a break, 10 minutes break, so we can re-meet again at 4:48. Okay. I have another question to answer, which is from Leonardo Zio. Why do we neglect the inductance term in the inductor model, but not in the capacitor model? Okay, so let me answer to this question by sharing the white screen. Okay, so here you have the model of the inductor. Okay, the model of the inductor is a, let me redraw here, composed by this parasitic inductance, which is given by the terminals. Then I have the nominal inductance. Okay, then I have the parasitic equivalent series resistance, and then I can have also a capacitance here. Okay, typically for most of the application, as I said before, the two capacitances that are in parallel here are, say, negligible here. Okay, so finally, we can say that more or less my practical model for real inductance is composed by two inductance that are in series plus a series equivalent resistance RL. Okay, but L, the nominal inductance, typically is very large with respect to L terminal. Okay, so if you have L plus L terminal, this is more or less L. Okay, this is the reason why I can neglect. So this is more or less L and RL. And for our next, let's say, consideration, I also neglect this one. Okay. For capacitance, the situation is a little bit different because even the L term inductance have the same values. Okay. Look at what happens for electrolytic capacitance here. Okay. Now, this equivalent series inductance, even if they have the same value of that of the inductance, now we get here a resonator. And even this very value, very low value, it can resonate with the nominal capacitance. This eventually goes to, say, megahertz range, depending on the value of ESL and C, because this FP is 1 over Q B square value ESL nominal capacitance, okay? And what happens is that it resonates. So we cannot neglect due to this resonance effect. Okay, this is the main difference. Okay, in the inductor situation, you don't have any resonance effect. Okay, I hope that I answer your question. Okay, so we understand that for especially for electrolytic capacitors, we have a equivalent series resistance, and this equivalent series resistance can lead to, let's say, some temperature increasing effect due to the current that flow through it. Okay, like any kind of resistance, when you have current flow through it, you can get power dissipation, then you can have overheating. And this is especially important for electrolytic capacitors because they are very dependent, the life, these electrolytic capacitors are dependent about the temperature, okay? So if you are able to not overheating electrolytic capacitor, maybe the life of this electrolytic capacitor can last longer, okay? So for that reason, anytime you have electrolytic capacitors, we have to choose the value, of course, but what's more important is to understand which is the equivalent series resistance. And so this is a parameter we have to, say, compute, or made better, to estimate, okay? Because it can lead to, let's say, to shorten the lifetime of the capacitors, can induce, let's say, decreasing in the efficiency, etc., etc. So this is very, very important. This slide shows you some basic information that you should already know about what happens when these devices are, let's say, in full conduction, when they are on, when they are at like on switches. So when I commanded it to be closed. For example, the diode can be represented by, let's say, the forward voltage drop. Okay. Again, there is also here resistance that can lead to some the effect, but more or less the voltage drop is much more dependent on the forward voltage drop V gamma that on the current flow. Can be very small. Okay, so the power which is dissipated when they are on, that is called the conduction losses of these devices, for the diode does not depend on the resistance. Okay, its voltage when they're on is almost constant. Okay, of course this is kind of an approximation, but in a first trying to design a converter can have, say, a certain you can grant in this kind of approximation. Okay, the same happens for bipolar transistors, in which when they are on, they can be approximated from the collector emitter terminals by a battery, which is the voltage DC in saturation region. The same happens for IGBTs. Okay, so for these three switches, one is the passive switch, the diode, into active switches, bipolar transistors and IGBTs. The conduction losses, the power dissipated when they are on, does not depend on the resistance. Okay, so almost voltage is the voltage is almost independent on the current, depends on the voltage. Totally different is the behavior of the MOSFET, in which when they are on, they can be approximated by the on resistance. Okay, and this on resistance, so the power dissipated when they're on depends on the current flow. It's not constant, depends on the current. This is should be quite clear now, because when we have to do with periodic waveform, what is most important is not like the instantaneous power. The power can change instant by instant. But what's more important in a periodic waveform is to compute the average power over a period. Okay, in our case, over a switching period. Yes. So the definition of the average power is given by this expression. P is equal to 1 over the period of interest, yes, in our case, the integral of the period of the product of the voltage and the current. So let's try to understand which is the average power dissipated in the on situation for these three kind of switches, in which when they are on, they can be approximated by a battery, and for a MOSFET, that when they are on, they can be approximated by the on resistance around. So for a constant voltage, this expression, which is the power, can be approximated by what? V over T now is a constant. Okay? And so since this is a constant, can be extracted by the integral, okay, can be Vd, for example, here. And so we have Vd constant, and then we have 1 over Ts of this expression, which is the average value of the current flowing through these devices. So the power dissipated when they are on is Vt, average value of the current flowing it. But the conduction loss for diodes, bipolar transistors, IGBTs can be always, let's say, defined in this way. The constant voltage, which can be the gamma for the diode, DC saturation, etc. for other devices, multiply the average current flowing to them. In a situation in which you have like the MOSFET or on resistance, when they are on, what happens that V, the integral of V multiplied I, voltage multiplied the current, the voltage is simply given by, oh my God, always a nightmare to write. Voltage is simply, let's say, ohm law. So we can say that if you get this expression, you replace this expression here inside the voltage of the integral, you can get Ron, the expression that is given in this parenthesis, 1 over Ts, the integral of I square T in the T. And this is definition of the square value of the root mean square. So in all the situation in which, like the MOSFET, in the on conduction, you can get a resistance, not a constant voltage. The average power is given by the resistance multiplied the square of the root mean square value. Okay? So that means that if you want to understand which kind of device you are going to buy, if you have diodes, you are interested also in the average current, not only in other characteristics like, for example, the peak current or the breakdown voltage of the diode, but also in the average current, because depending on the average current, you can have specific average power to compute and power converter to get, say, efficiency. For MOSFET, it's important to understand not only which is the maximum, minimum current, or let's say the average current, like other parameters, but also the root mean square value of the current, because it leads to the on dissipation, the conduction loss. So these are characteristics that we have to compute in what following. Okay, root mean square value of the current through the switch, root mean square value of the current through electrolytic capacitors, average current through the diodes. Okay, this is what concerns the conduction loss. So conduction loss are the power which is dissipated when the transistor and the switches are on. What happens when the transistors are off? So when they act like an open circuit, when they act an open circuit, of course, they are not ideal open circuits. Okay, so the current flowing through them is not zero. But anyway, we can say that the power dissipated when transistors or diodes are in the interdiction state, when they are off, is well lower the power dissipated when they are on. And so this kind of power can be negligible. So cannot evaluate no more in this course, in the examination, etc., which is the power off, the power dissipated when the switches are off. For me, for now, is zero. Okay, so we are interested in the power when the transistors are on, conduction losses, like the previous computed average power here. And another important parameter is the power dissipated when the switches, let's say, are commanded to turn on and turn off. So in the interval of time in which they change their status, okay, which is called the dynamic losses or switching losses. Okay? So let me just comment this slide, okay, that I prefer to comment here in the slide, not on the whiteboard, because there are a lot of graphs, as you can see here. So my goal is to give you some hints how to compute the power which is dissipated during the commutational states, from on to off and from off to on of the switch. So in order to do that, let's consider these simple circuits on the top of the slide, in which you have a power supply V, a constant voltage, a MOSFET. Here is a low, let's say, a low side transistor, so the source is connected to the reference voltage. Then you have the resistance on the drain, RL. This situation is not a realistic case for any practical switch mode converter, okay? But this is a start point for my discussion, okay? So suppose that here at the top of the slide here, you can see the VGS. Okay, this waveform is the voltage that you apply here to the control port of the MOSFET that command the status of the drain to source gate of the MOSFET. Okay, so depending on the VGS, the MOSFET can be commanded to be on or off. When VGS is higher than the threshold, the MOSFET is on. When VGS is 0 here or lower than the threshold of the MOSFET will be off. Okay? So suppose that this behavior is, let's say, periodically. So we have T on, T off, etc. Yes, is the period. So at the beginning, we command the MOSFET to be on, okay, because VGS is increasing. So this means that before the time instant 0, the MOSFET is off. When the MOSFET is off, it's like an open circuit. So the voltage VDS is the voltage V. And in fact, what happens here before 0 is that the voltage VDS is exactly the voltage V. Okay, here. The current is 0 because the MOSFET is an open circuit. When the MOSFET VGS is higher than the threshold, the MOSFET starts conducting, but there is a delay in this conduction. Mechatronics students that attended the lecture about the transistors should know that this happens because we have to, let's say, charge the input capacitance of the MOSFET, and this requires a certain amount of time. Okay? So there is a time interval which is called, let me just enlarge. Here there is a time interval which is called T on, this one, in which the MOSFET remains off. Okay, so nothing changes. The voltage is V and the current is null. Okay, then what happens that the MOSFET starts to conduct. Okay, the voltage VGS has, say, charged the input capacitance enough to make the transistor to conduct current, so the current increases. We have that circuits are resistance load. So as soon as the current increases, okay, the conduction of the MOSFET, say, goes on, and the voltage VDS goes off. Okay, so simultaneously, when the current goes on, the voltage goes off. Eventually, it happens that the MOSFET is fully closed, and so at the time interval T switch on, the MOSFET is on, and when the MOSFET is on, it's like more or less a short circuit, so the current is about V divided RL, okay, the current flow in the voltage is more or less, let's say, 0, or V on, because we have a resistance, okay, so it's not exactly a short circuit. So the MOSFET here is on. What happens during turn off? Here at this time instant, we have the VGS which goes to 0. The MOSFET instantaneously cannot go to, say, interdiction, because there is a delay time due to the fact that I have to discharge capacity, intrinsic capacities of the MOSFET. But eventually, the current goes down, simultaneously the voltage goes up, and then the MOSFET is again. Okay. Now, what happens in that situation? We have a TD on, which is the delay time to make the transistor conducting, and TD off, the delay time to make the transistor to, let's say, get into the interdiction. Then you have an interval of time, which is the time interval in this blue region, which is called TC on and TC off, and C stands for crossover, in which we have both the current and voltage across the MOSFET, which is different from 0, which are different from 0. So this crossover time is a time interval which can be very small or very large, depending on the MOSFET, depending on the circuit, in which you have simultaneously a voltage and a current from the MOSFET. You have power which is dissipated. And if you get the multiplication, you get, let's say, multiply voltage and current, these two voltage and current, you get the power, instantaneous power, which is dissipated by the MOSFET. And this is a parabola fashion, like this one, which gets the maximum, which is exactly at the mean of the interval. It is V squared over 4 RL. Okay, this is the maximum. This is a parabola. Then you have this term, which is V on, ion, which is the conduction loss previously I talked to you. Okay, the power dissipated when the MOSFET is on. It depends on R on and the root mean square value of the current. And then again, you have another contribution of power, which is given during that turn off. And then the power off, when the MOSFET is off, is negligible, as I said before. As you can see, this term, this contribution during the turn on and turn off can be quite large. Okay? And this, sometimes this, I can say most often, most of the time, this can be the dominant contribution of dissipation in power transistor. Okay? So, how can we get a way to compute the power loss, okay, the average power across, let's say, the period Ts, because we are interested in the average power and not in the instantaneous power. So if you look at the area under this parabola here, the area under this parabola is an energy, okay? And then you have two parabolas here, which you have an energy which is lost during the turn on, energy which is on during turn off. So you have two energies contribution for period, which is the area of a parabola, because now we are interested in computing this area. Okay, the area of a parabola is 4/3 of the triangle area, which is under the parabola. Okay, so 4/3 of ABC triangle area. So let's compute this using this formula, the energy under, for example, this parabola here. The base of this triangle is the crossover time, TC on. The eighth is V squared over 4RL, and the triangle of an area which is 1F base multiplied 8. Okay? And so we have this contribution multiplied 1F give you, say, 2 divided by 3, because we have 4 divided here. The same contribution happens for T off. Exactly the same. TC off now, the 8, which is the same, multiplied 1F. So this is the energy loss totally during a period. You can say that it's some simple, say, multiplication. Okay, we say that V divided by RL is the on current that flows when the MOSFET is on. Okay, So this current is V square over RL here is the this contribution here is I on. Okay? And so I can say that 2 and 4 can be simplified, giving you 1/6, and then I can get this expression here. This is the energy loss total in a period. Always in a computation like this, you can recognize that the energy loss has a factor which is given by the shape of the power. It's in a parabola and gives you 1/6. Then you have the summation of the crossover time for P on and P off. Then you have the voltage V when the MOSFET is off, okay? And you have the current when the MOSFET is on. Of course, this is the energy. In order to get the power, you have to average the power during the period. So divided the energy by Ts, so multiply Fs. This is the power loss energy multiplied by. So it depends on the frequency. If you are increasing the frequency, the switching frequency, you get higher dynamic losses. So think twice about the maximum frequency you can use, okay? It depends on the transistor you're using, but also depends on the maximum dissipation loss you can admit in your application, okay? As I said before, this is a situation that do not happen often in practical switch mode power conversion. Okay? A situation which is most common is a situation which is depicted here. In this case, the circuit is a little bit different. But if you look at the circuits, you can recognize the basic elements, the basic components that always are inside any switch mode power converter, which are the switches, the inductor. This is why these circuits is, say, most useful in power computation, power estimation that the previous one. Okay, in these circuits we have a MOSFET, we have a diode here, and we have an inductor. As you can see, these circuits here is what I call the switching network. Remember the switching network that I described as a basic building block of the BAC. Okay, it happens also here. For mechatronics students that follow the components and transistor lectures, this is a circuit that already has been discussed. Okay, in that case, the cathode of the diode is connected here. Okay, but the situation is always the same. Okay, now we have another voltage supply V2, which is not V, but in the case V2 is the same of V, the circuit is exactly the circuit that they analyzed during that lectures, in which the diode is the freewheeling diode for the inductor. Hypothesis here is that the crossover time is so short, so the time interval which you have the commutation of the volts and currents is so short that in that specific interval, the inductor can be considered as an inductor, as a current source. So they hold the same current. My circuits that I'd like to analyze is one. So again, the voltage VGS can say made to be periodic. At the beginning of this analysis, the MOSFET is off. So what happens when the MOSFET is off? When the MOSFET is off, all the current I goes through the diode here. Okay. So which is the voltage VDS? The voltage VDS is exactly the voltage V2 because the diode is on, so it's a short circuit, and all the voltage V2 appears across the VDS. And so we have V2 here at the beginning. Current through the MOSFET is zero because the MOSFET is off. Then what happens when I have VGS, which is higher? Of course, we have a delay time, which you have to charge the capacitance, etc., etc. Eventually comes the situation in which the VGS is higher than the threshold voltage, and what happens is that the MOSFET starts to conduct. Start to conduct means that the current increases. Okay, the current starts to increase. What happens to the diode in that specific situation? But the current in the diode, which is this one, the diode let me share the whiteboard because it's more simple to me that I do write on that slide, which is impossible. The current source the MOSFET diode VC. The current I diode is what? This is the current through the drain of the MOSFET. This is the current I. So the current is I minus I drain of the MOSFET. Okay. The current of the drain is increasing. Okay. Is increasing, but the current I, supposing that is at this level. Since in this drawing, the current ID is less than I, okay, since this current ID is less than I, the current I diode is positive. And so that means that the diode is on. Okay, so up to the point in which the current ID reaches I, the diode is on. So for this time interval, diode is on. And when the diode is on, the voltage VDS should be equal to V2. There is no way. The diode clamps the voltage across the MOSFET to be V2. Okay, so the voltage VDS, if you want, is constant up to this point. Only when the current through the drain of the MOSFET reaches I, which is the value here, then, and so I diode is 0, the diode becomes off. Here, the diode becomes off. And when the diode becomes off, then the voltage VDS is no more clamped to be V2, it can go down. And so, respect to the situation in which the load was a resistance, okay, now there is, let's say, a shift of the voltage VDS toward left. If you look at the multiplication of the two in order to get the power, okay, if you want to multiply the two to get the power, I drain multiplied VDS, which is the power, versus time, you have that 0 up to a certain point here, then linearly increase, like the current, then at this point it goes down. Though we have no more the parabola waveform that we get in the previous situation. We have a triangle. Okay? We have this triangle here. The same happens, of course, for the Bruno. So now the shape is different, which is the peak of the instantaneous power, is the voltage VQ, which is the maximum value here, multiply the current I. So V multiplied I. Which is the time duration? Time duration is now this crossover time, which is the time in which you have both current and voltage, which is different from zero. Now the area, so the energy under this triangle is simple to compute, which is simply the area of this triangle, 1F, Tc on multiplied V2 and I, okay, Tc on, which is the base, the A is V2 multiplied I, and the same for the Tc off by V2I, okay, divided by G. Again, we get a shape factor, which is now 1/2, not 1/6, so it's higher than before. the crossover times, and then multiplication of the voltage when the MOSFET is on, the current when the MOSFET is voltage when the MOSFET is off, the current when the MOSFET is on. The power loss again is the average of this energy to a period S. Okay, so let's consider that the shape factor now is higher than before. This is what happens for that situation I described to you. What happens here is that I consider that for both the transition that is turn on and turn off, the voltage is always the same, V2 here and V2 is here, and the current is always the same, I and I here. Okay? But let's have a look to the MOSFET current. Okay, remember which is the current flowing through the MOSFET in the back circuit, for example. Let me, it's this one. Okay, this is the current flowing to the MOSFET. Okay, switch current, which is like the inductor current when the MOSFET is on, is 0 when the MOSFET is off. Okay, so during the on, the MOSFET is on. Then, so here we have the turn on, and here we have the turn off. So I can apply that kind of expression, okay, to this switch current. Now the switch current has two different currents. One is I minimum, and the other one is I maximum. Okay, they are different. So the situation is not exactly the same as described here, in which the current are the same, because now the situation is more, say, similar to this one, in which the current are different. But even if you want to look at the voltage, you cannot have the same voltage across the MOSFET. Because when the MOSFET is off before turn on, typically the voltage is not the same when the MOSFET is off after turn off. Okay? As you can see here, we have two different voltage levels. Okay? We have not the same voltage level here. They are different. There is a difference here. Okay? Why do you have this kind of behavior? Because typically in this transition, okay, you have the I on the T, okay, here and here. The I on the T here is positive. The I on the T here is negative. Since typically you always have some parasitic inductances due to the printed circuit board, due to the terminal of the MOSFET, whatever, when you have metallic traces, always they have inductance. Serious. This kind of the I on the T induces a voltage drop across these inductances. And the sign, the polarity of this voltage drop is different depending on the I on the T. When the I on the T is positive, okay, like during turn on, the voltage drop across this parasitic inductance here is positive. And this means that the voltage drop to the S is lower because it is clamped by V2. So the total voltage here is V2 when the MOSFET is off. But since now we have this voltage here, which is positive, the voltage, true voltage across the MOSFET is a little bit lower. When the I on the T is negative, this voltage drop has a polarity which is this one. And since V2 appears across these two terminals here, it means that the voltage VDS across the MOSFET is a little bit higher. So, in other terms, we can apply this expression here, which is always true for any kind of buck converter. You can pretty rely on this formulation based on this circuit, okay? And which gives us this kind of expression, which is this shape factor and this voltage account. But we have to modify a little bit the current through the MOSFET because it's not constant, because we have an inductance that shape that triangular way the current. And then you have to consider that typically inductances can modify the voltage level when the MOSFET is off, before and after turn on and turn off. Okay? So if you take as a more general situation the case in which you have different current and different voltages, and they name this current I after, so the current after the turn on, I before, the current before the turn off, and V before in the opposite sign. So V before is the voltage before the turn on, and V after turn off. We can have a little bit slight modification of this triangular waveform. If you recompute our area I did before, with this slight modification in the values here, you can have these general expressions. 1f, this is a shape factor, always the same, triangular waveform. Switching frequency, okay, because we get that average power dynamic loss. Multiplication of TC on, so the crossover time during T on, V before, current after, TC off, V after, I before. Okay, look carefully this expression because we can use this expression for the computation of the power losses in future exercise. Okay, so maybe we can also practice this equation during exercise. Okay, of course, this is kind of estimation because the crossover time are not always so precise, estimated by datasheet. Okay. The same happens for the voltage after and before because they depends on some parasitics, which value nobody knows. So I can call this kind of computation not a real computation, but it's an estimation. Okay, pay attention to this estimation. Maybe we can exaggerate a little bit on the value in order to overestimate these losses because it's always better than underestimate them, but it's always an estimation. Okay. This estimates the dynamic losses that, together with the conduction losses, can provide us a, say, good, number for estimating, for example, the efficiency of the converter. Okay, questions about this computation? So, in all this discussion about the real components that you can use in your power converter, it should be quite clear that we have not only to compute the, say, nominal current, like for example, the peak value, the peak-to-peak value of the inductor current, or say estimating the inductance as I said before. But then we have to also compute some other parameters that are useful for choosing components from datasheet. Okay. For example, anytime we get resistance, parasitic resistance in our component, electrolytic capacitors, MOSFET, for example, we have to also compute the root mean square value because they lead to some, say, dissipations that we have to understand. Okay. So let me continue this lecture by defining some methods by which you can compute sometimes in a rigorous way, some other times in an approximate way, the root mean square value of the currents flowing in the various branches of the converter. Okay. I need to share my whiteboard to do that. So, as I said, capacitors and electrolytic capacitors have ESR. When we have ESR, we have to compute the root mean square current because the root mean square current, together with the resistance contribution, gives us power dissipate, which is transformed in heat. And the heat in electrolytic capacitance is a very important environmental parameter that leads to reduction of the life, operational life, or to enlarge the operational life, depending on the value you can operate. So let's start with the input, the C0 capacitance, so the output CNOT output capacitors. Remember, which is the waveform of the output capacitor is the same of the inductor capacitor, which is our triangular shaped wafer, minus the average value of this capacitance, because the output capacitor and the capacitor in general have no DC current flow to them in steady state. And so it's something like this. In which this is TS, and this is T-on, for example. These quantities here is delta IL, so the peak-to-peak value of the inductor current. This is the inductor current, which is rigidly translated, okay, up to the point which the DC value, the average value, is null. Root mean square value of this current. We have to compute this. Root mean square value, which, what does it mean? Which is root mean square. So, as a first step, we have to, the definition is something like this. IT over the period I square I naught. This is the IC root mean square value. Okay, so as a first step, we have to square the current. Okay, so let me square IC naught. To square this, you obtain just a totally positive. If you square something which goes linear, you can get something like this, say, portion of a parabola. Sorry. When it's negative, of course, when you square it, you can get something which is positive. You get 0 here, and you get something. Okay? Which is the maximum value? The maximum value is, if this is delta IL, these quantities here is delta IL. This quantity here, the total positive quantity, is delta IL divided by Q, so this is delta IL square value. Okay. How many of these parabolic triangle we have in a period Ts? But this half here gives us one of this parabolic triangle, and so we have Q parabolic triangle. Sorry for giving that name, but I don't know how to call them in Ts. Okay. This is the square. Then I have to, let's say, I have to get the integral. Okay, so you have to get the, you can see here, you have to get the integral of this square value. In order to get the integral of this square value, means that you have to compute the area under this parabolic triangle. Okay. So how can you get the parabolic triangle area? So now we can use some old Greek theorem that says that you have a kind of parabolic triangle, then you want to get the area under this parabolic triangle, then you have to use the rectangle which encloses this parabolic triangle here, and this rectangle has an 8 in the base, and the area is area of rectangle is h multiplied b. Okay, so the area of parabolic triangle is 1/3 of h multiplied b. So 1/3 of the area of the rectangle that encloses the parabolic triangle is the area of the, which is our base. But if you look at this waveform here, the base is exactly this portion here. But this portion is Ts divided by 2. The 8 is this one. So the area in our case will be Ts over 2, and the area is, the 8 is delta L divided by 2 square bracket. So in our case, the area of the triangle, parabolic triangle, is 1/3 of Ts divided by 2 delta EL. Okay. Now we have to get the mean value. So we have to average over Ts. How to get the average over Ts? In order to average over Ts, you have to get how many of the triangles you have in a Ts. I said they have two parabolic triangles in Ts. So you have Q area of parabolic triangle in Ts divided Ts. So I have 1 over Ts of 2 times what I computed here. 1/3 of Ts delta EL squared over 4. Ts and Ts can be simplified. So delta EL squared over 12. This is the IC not square root mean square value. So the square value of the root mean square current. Okay. If you want to get the ICO root mean square value, you have to get the square root of this, so delta IL over square root of 12. This is the root mean square value of the output current. Delta IL is something that you already know. Okay? Delta IL is VO over L 1 minus D over Fs. Okay. Of course, if you want to get this the maximum value of the root mean square value, the square current, you have to consider the delta IL maximum, so that you can have for the minimum, for example. Okay, when you get the minimum, so the maximum input voltage, you get the maximum delta IL 50 current, and so this brings to you that maximum root mean square value of the output capacitance. Okay. Questions about this kind of computation, which is reported here. Okay. Problems, questions about how computed? Just simply theorem for the parabolic triangle, something like that. This time the computation is exact. Okay, so what we get is the exact value of the square. Sometimes in the future, I can just use some approximation because computation leads to some complicated formulas that I don't employ. Okay, so let me share again in order to say, gone with this root mean square computation. And I'd like to point out an important question, is that Kirchhoff current law, up to now I apply this Kirchhoff current law for instantaneous value of currents, so the current that changes time to instant to time instant. And then I applied Kirchhoff current law for average value. Remember all my computation that I did for computing, say, the current in the input and output capacitors and being derived from a Kirchhoff current law that was computed taking into account just the average value of the current flowing in channel. My question now is that is it possible to employ the Kirchhoff current law for, say, the root mean square value of currents? So, supposing that I have, say, at the node k currents, and these currents are expressed in terms of their root mean square value. Is it possible to say that the sum at this node of these k currents that are root mean square current is zero? Is it possible to say that in the same way we did for the average or the instantaneous value? The answer is no. The answer is not, because this time the root mean square value, by definition, is not a linear operator, because we get the square value of the current. So this kind of application without any modification is not possible. So for root mean square value of values, this is not possible. Instantaneous value, yes. Average value, okay. They are linear operator, root mean square current, no way. So let me show you a situation that most of the time happens in power converter. For example, the buck and all other converters. The situation is this one. Typical situation that we can make in power converter. Let's have a node. Okay. I don't know what is the components connected to this node, but what I know is that here I have a current I. Here I have a current which is constant, so DC. And here I have a current which is just AC. Look at the capital letter for indicating DC quantity, and the small letter, okay, and small also subscript to indicate something that is just AC. So here you don't have any DC. Here you don't have any AC. Of course, I, which is by the instantaneous Kirchhoff current law at this node, you can have the instantaneous expression like what I said here. So E is I is IDC plus IAC. This is simply possible to write. So I is a current that has at the same time AC plus DC contribution. DC is just DC, AC is just AC. Okay, so we have a current which has both AC and DC terms as a summation of a current which is just DC current and a current which is just AC current. Okay, this is a situation that can happen most often in power converter. And now look at what happens if we compute the root mean square value of this current I. Okay. So let's compute the root mean square of I root mean square value by definition is 1 over Ts in a period Ts of the summation IDC plus IAC square value. So this is equal to 1 over Ts. Let me say develop this square, so IDC square plus IAC square plus 2 times AIDC multiplied. Okay. So the first term is 1 over Ts integrated over Ts of IDC square plus 1 over Ts integrated over Ts of the AC contribution plus 1 over Ts of 2 times 0 Ts IDC multiplied IAC. So I separated the integral of the sum in the sum of integrals because it is a linear. So this is a constant term. I can put an external of the integral, and I can integrate, and I keep IDC. Plus, this is the definition of the root mean square value of the AC current. So this is the root mean square value of the AC current. Plus, here I have 2 times IDC, which is constant, so I can take out of the integral, S over EIC. This part here is the definition of the average value of AC. But the average value is null by the definition, because I define IC a current which has no DC, and IDC a current which has no AC. Okay, so this integral goes to 0. So as a result, I have that the root mean square value of the current, which has both AC and DC contribution, is the summation of the square of the DC contribution plus the root mean square value of the just AC contribution. Note that this is a fundamental result that is also called quadratic Kirchhoff current law. Okay, so we cannot apply the Kirchhoff current law for just root mean square value of currents flowing in the nodes, but we can apply the quadratic Kirchhoff current law when you have a current which is the sum of a DC current and a just AC current. Okay, in this way. Why we are interested in this kind of exploiting this result? When and where in our buck converter you can have a, say, a situation like the situation I described and that lead to these results. For example, look at what happened at the output of our converter, where you have the inductor, and then you have the capacitors, and then you have the load. This is the filter at the output of our converter. Okay, then you have the diode, etc. We are not interested, just interested in the output node. This current flowing to the load is I naught. This current is DC current. No AC contribution here. Okay, we have a DC-DC converter, so the output current is simply V naught over R, and so is the current here, IC naught, is a current flowing through a capacitor, so no DC component. Just AC current. The current flowing here, the current IL, is, as a consequence, the sum of what? IL over T is IC naught plus I naught. IL is a current composed by IC plus DC contribution. IC naught is just AC. I naught is just DC. So exactly the situation I described in previous way. So I can compute applying the Kirchhoff current law, quadratic Kirchhoff current law to out node, the root mean square value of the inductor current. The root mean square value of the inductor current is the square value of the DC current plus the root mean square value of the IC naught current. So is I naught square value, which is the root mean square value of the IC naught current. We computed a few pages before here. Delta L divided by square root of 12. So is delta IL square divided. This is the expression for the root mean square value of the inductor current. Okay. Of course, you have to put here delta L, then you can delta L is the specific expression that is P over L 1 minus B divided Fs, etc. But delta L is also what? Delta L is the ripple in the current. The inductor current. Okay? Is the variation of the inductor current. Typically, and remember that the average value of the inductor current is I naught. Typically, in CCM design, I naught is much larger than delta IL. Why? Because this is a means to reduce the stress of components. Okay? Remember, for example, the root mean square value of the I naught capacitor depends on delta L. It means that if delta L is very large, the root mean square value of the output current is large. And this is a parameter that leads to, let's say, some drawbacks, okay, because it leads to overheating of the capacitor, so shorten the life of this capacitor, etc. So in order to get to less stress in the output capacitor, for example, delta L should be very low, okay, should be minimized. And delta L is the same of the inductor current. So then I show you next time another reason why I want to get delta L very small. Okay. So what I can say that is always true that in a well-designed CCM buck converter and all other converters, that the ripple current in the inductor is always much less than the nominal output current. So that means that a good estimation of the root mean square value of the inductor current is that this is constant to the output current itself. Typically. Okay, so this is a very good situation. Typically, delta L, just to give you some numbers, delta L is a few percent of the maximum output current. Let's say 10%, maybe 20%, or even less of maximum output current. Okay, and so if you think you have in mind this kind of situation that reduces the stress of all components and will give you another positive situation that I describe you later, then the root mean square value of the inductor current is the same of the output current. Okay. Which is another component that needs to know that the root mean square value of the current, the switches. Switches when you want to compute the root means the conduction loss. The conduction loss of the switch are R on multiply the root mean square value of the switch. Remember what I said before. So we need the root mean square value of that switch current. The switch current is something like this, like the IL when the transistor is on, etc. We commented on this waveform several times before. If you look at the inductor current from which this waveform, say, is obtained, okay, the inductor current is the same, then goes down, something like this. This is that, and the average value is I naught. Okay, so the average value is the value in between I minimum and I maximum. Okay, so average value of the I naught is something like here, like value. Okay, same. So we have to compute the root mean square value of this current. There exists some precise equations. If I remember well, at the bottom, very bottom, the last slides, I put all the equations that are maybe exact equations into this equation. I don't remember what I have to check. Sometimes they are very complicated equations to get the same result. So here I get approximate results based on the approximation hypothesis. The hypothesis is called the flat top approximation. Flat top approximation means that instead of having this waveform, which is a waveform that has the slope over there, I can approximate the waveform in this way. Let me change the color. Green. As a rectangular waveform. This way. So I flat the top. And the value here is I naught. So I choose the average value here of this slope as, say, top level approximation of this curve. Okay? So in that way, I can compute the root mean square value in a simple value, simple method. I just have to square this value. Okay, so let me square it. Okay, let me square it. There is something not working with. Okay, now it's better. I switch square value. And so we have a rectangle, so that means that we have I naught square and then 0 when time is 0. Okay. Then I have to consider which is the area. Remember the same steps we did for the parabolic triangle area. The area is I naught square multiply by the duty cycle, the area over PS. Sorry about the bad screen. I don't know what happens, but maybe something strange with my. So if I get the area and average this area over a TS, so I get this value here, okay? And the root mean square value is simply the root of this value. So this is I which I switch root mean square value square. So I switch root mean square is simply I0 square. Of course, this is an approximation. Next time, which is Tuesday, 8:30, okay, we can just compute the root mean square value of the input capacitor curve, which is the other variable we need, other component we need the root mean square value to be computed, and get some, say, concluding remarks about the diode and the MOSFET, and we can pass to the DCM. Okay. Next week I have lecture on Tuesday morning, and then also Friday morning at 10. Friday morning will be devoted to an exercitation, okay, design of a buck converter CCM. On the Friday afternoon, then we get the laboratory, okay? Stay tuned on the portal for news. If you have something to ask me, don't worry about them. You can ask me anytime, even now or later. And if you have no question, I can say stop here this lecture. Okay, thank you very much. You have a nice weekend.